In this tutorial video, you will be learning on how to model carbon fiber reinforced epoxy structure for frequency response function by using modal and direct frequency response. The steps required on modeling the CFRE composite plate are shown as follows. For this case study, thin plate of CFRE structure are modeled by using the material properties shown in the table. The dimension of the plate are as shown in this table, where all the dimensions will be in unit of millimeter. To create the model, click the Geometry tab. Change the option Object to Surface and Method to use as XYZ. Next, for the vector coordinate list, insert the dimension of the plate. Click Apply. Next is to discretize the thin plate into several elements and nodes by doing meshing. Click Meshing and change the object to Mesh. Choose Surface 1 as the surface list. At the Mesh Size option, change the value to 10 mm. Click Apply. Select Load Options and click Force. Insert Force as the new set name. Click Input Data and insert 001 in a force column. Click OK and select the application region. Change the Select option to FEM. Select the node at the left end of the structure, click Add, OK and Apply. To see the force exerted, change the orientation at the Home button. To create the properties of the plate, click on Properties tab, then choose Isotropic option. Label the material name to CFRE, then input the properties of material according to the previous table value. Click OK and Apply. Next, we want to set it into 2D properties. Select Shell and insert Property. Set Name to Plate. Click Input Properties and choose the material name at the Material Property Name option. Then, insert the thickness of 2 mm. Click OK and select Application Region by selecting Surface 1 as members. Click Add, OK and Apply. Next, we can do the analysis of the entire model. Extract the frequency response function using Modal frequency response analysis. Select the solution type and choose frequency response. At the solution parameters part, click Eigenvalue extraction and select the frequency range of interest. Here you can enter the lower and upper frequency and the desired number of root that we are interested on. Change the output format to XDB format. At the Subcases column, choose Default Subclass Parameters and define the frequencies. At the Subcases Select column, click Default, OK and Apply. Wait until the analysis is done. More elements will take longer time to run the analysis. After analysis is complete, attach the XDB file. To review the result, click on the Results tab. Choose Graph as the object and click the Select Result Cases. Click Filter, Apply and Close. Choose Displacement, Translation column and Z component. As for the target entities, select the nodes that we want to execute the FRF. Use log as the y-axis scale and magnitude for the complex number. Click Apply. Here you can compare the FRF of other nodes to find the appropriate FRF driving points. This refers to point that contain all the resonance peaks in the FRF within the frequency of interest. As for this study, node 31 is the best FRF as it contains all the resonance peak. Extract the frequency response function using direct frequency response analysis. Select the solution type and choose frequency response. The steps is basically the same as modal frequency analysis, but difference is by changing the mode to direct instead of modal. Change the output format to XDB format. At the subcases column, choose default subclass parameters and define the frequencies. At the subcases select column, click Default, OK and apply. After analysis is complete, attach the XDB file. To review the result, click on the Results tab. Choose Graph as the object and click the Select Results cases, click Filter, Apply and Close. As for the target entities, select the nodes that we want to execute the FRF. As for this study, node 31 is the best FRF as it contains all the resonance peak. Hopes that this tutorial could be useful and helpful for students, or engineer, or researchers who are involved in modeling of a CFRE composite plate. Thank you for watching.